on behalf of my co-chairman, I would like to open the session and to invite Evelyn Telfer to give the first presentation. And Evelyn Telfer is Professor of Reproductive Biology, Institute of Cell Biology and Center for Integrative Physiology, School of Biological Science, University of Edinburgh, Scotland, United Kingdom. And she will give us a talk entitled, Can We Learn to In Vitro Mature Primordial Follicles? Please.
Okay, thank you very much, Seth, and thank you to the organisers for inviting me here. This morning's session has been really stimulating, and I think the last talk by Arthur was really thought-provoking. So it kind of informs a lot of the things that we will talk about in the next few 2 days. So my title that I was given was, Can we learn to mature primordial follicles in vitro? And the answer is, yes, we can. So I'm now going to tell you where we are with that and maybe, what the future of that type of technique is. So my declaration then, I have no conflicts to declare with this aspect of this work. So in terms of fertility preservation then, we've heard a lot about this, and there's various options for fertility preservation in women. But for young girls, really at the moment, the only option is in terms of taking a small piece of ovarian cortex and freezing it. So ovarian tissue cryopreservation. And this is something that's been going on now for a number of years, and there's clinics all around the world that have stored ovarian biopsies from young women. So what can you do with that? And at the moment, the only option really is to transplant the tissue. But of course, that may not be an option for many of these young women, particularly if the tissue has cells that could be, tumorigenic, so you wouldn't want to transplant that type of tissue. But this tissue contains predominantly primordial follicles. And you see, when they take the cortex, if you examine it histologically, there are many, many primordial follicles present there. So in terms of course, from the point of view of learning about human oocyte development, then it would be a good system to have in vitro grown oocytes to look at what factors regulate the process, but also from a very practical point of view, in terms of fertility preservation, being able to grow these oocytes all the way from that early stage right through to the point where they could be matured in terms of their meiotic and cytoplasmic maturation, and ultimately fertilisation and embryonic development. And of course, that is a whole different area, and we would then get into the moral and ethical issues. But let's just see where we are with this type of technique at the moment. So of course, you start with an animal model. And culturing follicles has been going on for really a long time. Almost 30 years in terms of looking at animal models, the culture of ovarian follicles has taken place. The culture starting from the most immature stage, from the primordial, has really started about the mid-1990s. And most of the work was carried out in the Jackson lab up in Bar Harbour, Maine, in John Epig's lab. And what they started to do was to take the whole mouse ovary and then to take it into pieces, put it into pieces, and activate the growth of primordial follicles. And they were able to achieve the complete in vitro growth using a 2-step culture system. And in their first set of experiments, they had one mouse. And that mouse was Egbert. And this is Egbert here. And Egbert was an example of when Arthur Kaplan spoke in the last talk about when things go wrong, how that can set back the development of a technology. And Egbert was what went wrong. Egbert was a fat, lazy mouse, and that's not normal for a mouse. And when Egbert died, they looked at his tissues, and he had lesions in almost every single organ system. So there was a conclusion made that the reason for Egbert being the way he was due to some problem in epigenetic programming during the in vitro process. No evidence for that at all, nothing. But that was a conclusion, and of course it then set back culturing follicles from the primordial stages, particularly in larger mammals and, of course, in humans. But EPIG went on and they developed their methodology further, and they can now produce lots of offspring, and there's not been any more egg births. So we don't know if egg birth was a random event, which it happens, or if it was related to the culture conditions that he was using at the time. But improved culture conditions have shown that animals can be produced, mice can be produced, and they're healthy animals. So we now know that you can grow follicles all the way through from the primordial stage, and we now know through the work of the Japanese group, and Murahaku has developed a very, very nice culture system starting even earlier than primordial follicles, starting from primordial germ cells, and has defined the factors that are required to coordinate development all the way through to meiotic maturation, fertilisation, and development of live offspring. So we have a proof of principle that we can grow primordial follicles up to that point. But that's in the mouse. So this is a complicated process. It's not a simple thing to do. To recapitulate oocyte development in vitro, you have the primordial follicle, which is arrested, the dictate stage of prophase 1 of meiosis, surrounded by a few flattened granulosa cells, so held almost like in suspended animation. And then these follicles, these primordial follicles, will start to grow. They'll be activated to grow. They'll increase in size. They have to stay in meiotic arrest. They have to acquire the ability to resume meiosis. They have to acquire developmental competence, so many cytoplasmic changes. They're undergoing transcription. Then there'll be transcriptional repression later on in development. And of course, genomic imprinting is going on. And this all goes on within the context of the ovarian follicle. So it's a developmentally regulated process. The follicle reaches a preantral stage, the antral stage, and then the point where you have the mural granulosa cells and the cumulus granulosa cells, you would have a oocyte that may be developmentally competent. So a lot of different processes going on and difficult to achieve in vitro. So we've been working on developing culture systems for larger mammals and also for human. And I'm going to talk to you about what we can do with our human system. So with the human system, we've developed what we would term a multi-step culture system. So of course, one size doesn't fit all. We have to change depending on the stage of development that the follicle is at. So we start with optimizing the growth from the primordial stage within the ovarian cortex, and then supporting the development of the isolated growing follicles. And then looking at the oocyte itself and its surrounding cells, optimizing the stages, that stage of development in order to determine whether we can get meiotic maturation. And then, of course, it's our goal to test the function of these oocytes, and particularly in terms of fertilisation and then testing the embryos or any embryos that we may get. At the moment, we cannot do that because of regulatory requirements, but it's something that we are hoping that we will get permission to do sometime in the near future. So with our human system then, of course, we need human ovarian biopsies. And we get these biopsies from various sources. So our clinical collaborators are Richard Anderson and Hamish Wallace, who's a paediatric oncologist. And Richard and Hamish have really organised the Fertility Preservation unit in Edinburgh. And we get tissue through informed consent at the time of caesarean section, and we've had that from women, relatively young women, very young girls from the Fertility Preservation programme, and of course sometimes gynecological procedures. So we do have a range of tissue, and we've been able to get tissue from as young as 15 months up to 49 years. So, a good age range to study this process. So when we get the tissue, we form what we would refer to as a microcortex. Now, the most important feature of activating primordial follicles in vitro is the way the tissue is treated. The tissue has to be stretched in a way that almost wakes up the primordial follicles, and we remove a lot of the underlying stroma cells so that any inhibitory influences are taken away at that stage. And what happens is that we have many of the follicles that are present are activated to grow. So we can see lots and lots of primordial follicles that have started to grow, and that happens quite quickly. That happens, within 1 day of putting them into culture, we have activation of these follicles, and within 6 days we can see preantral follicles. And this is a histological section showing you a multilaminar follicle, human follicle, nice granulosa cells, and seem to be maintaining the contact with the oocyte, and the oocyte in this case does look healthy. So what we do at that stage then, we can't leave these growing follicles within the cortex. Now, what I should point out to you is that primordial follicle activation will only happen if we keep them within the cortex. If we try to isolate primordial follicles, they will not grow. They just sit around, they don't do anything, but to get them to activate, they must be within the cortex. But we have to manipulate that cortex to activate their growth. And we see then that we can dissect out growing follicles. And the reason we dissect out the growing follicles is because if we leave them within the cortex, there's degeneration. And that's what would happen physiologically. These follicles would start to talk to one another and would inhibit the development of one another. So obviously in a human, there's only one that would reach the dominant stage and ovulatory stage. So we're sort of taking them away from a repressive environment and culturing them individually to maximize their chances of producing a developmentally competent oocyte. So that's what we see. We can see these growing follicles within the tissue, and we manually dissect them. We don't use the enzymes for this. So in our hands, enzymes are bad for the follicles. So this is what we would dissect out, and we always have some theca cells present, because if you remove all of the theca cells, the follicles don't survive very, very well. So if we then grow them individually, again, within a relatively short period of time, we can obtain antral formation. We see antral follicles formed, and this is in the presence of a defined media. It's a serum-free media. It's a very low dose FSH, and it has activin A there. And these follicles develop antral cavities, and you can see that the oocyte maintains its connection with its surrounding somatic cells, which is key to their survival and, getting them through to the next stage of development. So this is our multi-step culture system so far then. We have the activation of the primordial follicles, and then we dissect the preantral follicles out. We grow them individually, and these retain their three-dimensional configuration. They're not flattened out in any way. And then, of course, we've been working on developing the next stage of development, trying to get those oocytes to the next point where they might be capable of maturation. So our approach has been different from many other groups. Of course, there's other groups working on the in vitro development of human follicles, and the group in the United States is the group of Teresa Woodruff in Northwestern in Chicago. And they've been working on a system where they've been taking preantral follicles and growing them for a very long time and maintaining the whole follicle. But we're more interested in this part of the follicle, the oocyte and its surrounding cells, because the whole follicle also has an endocrine function. And we would really be interested to see if we can take the oocyte, the surrounding cells, out with this environment and mature the oocytes appropriately then. So that's what we've been doing. we've been taking these antral follicles that we achieve by growing the primordials in vitro. We take out the oocyte with the surrounding granulosa cells, and then we grow them on membranes for the further period of time until they've reached almost mature size for a human oocyte, and then we test their capacity for meiotic maturation. And what we find is that when we put them onto the membranes, they do undergo a period of growth, they increase in size, but it's in a relatively short period of time. There's no point culturing them for much longer than 4 days on these membranes. So if they don't get to that size by that time, then they are degenerate. So we only take them between 2 and 4 days on the membranes. And then we would take those oocytes and their surrounding cells and put them into maturation media. And this is the kind of stumbling block, this whole process of the meiotic maturation phase. And what we find is that when we do the imaging, and this is some of the imaging that was done by David Albertini, we find that there's a whole range of morphologies of oocytes. And some of the oocytes have their germinal vesicle still there, and some of them have formed spindles, but they're abnormal. They don't look good. So we have a range of types there. But what we do find is that we also have oocytes that resume meiosis. At least they show a metaphase 2 spindle here, and they show a polar body, which in this particular example, the polar body is larger than you would normally get in the oocyte. So these are things that we're looking into, and we're of course modifying our media and our culture system. But this has given us some hope that there is the proof of principle that we can get some of them to reach metaphase 2, and maybe by altering our culture conditions, we can improve upon that. So that's where we're at the moment. So summarising our system then, we have a system, multi-step, that we can get oocytes to reach metaphase 2. And it's about 30% of the oocytes that survive the culture, not of what we start with, but the survival, the ones that actually do survive. So there's a kind of self-selection process. But of course, we're looking at our media formulation, and we may improve on, or we hope that we'll improve on that. So in summary then, this multi-step culture system supports human oocyte growth and development. Of course, optimisation is required at each stage, and further testing is required. There's no question about that. But the real question is in terms of its utility. Of course, from an academic point of view, we now have a model system for human oocyte development. But from a practical point of view, could this technology or this technique be used in fertility preservation? Now, as I said to you right at the beginning, the patient group that would benefit from this most is the young patients, the prepubertal girls. And so I'm going to show you some work that we've done using tissue from prepubertal girls. Now, in the mouse model, all of the mouse models are prepubertal. Everything's prepubertal. There's nothing that's been done in adult mouse. So they're prepubertal primordial follicles that have been activated, they've grown, they've had lots of babies. So the question is, can we develop the oocytes from the primordial stage in prepubertal girls? And this was a study that was done, and was young girls that were coming into the fertility preservation clinic, and they had different diagnoses, and they agreed, or their parents agreed, to have a piece of the tissue that was getting taken for cryopreservation, a piece to be taken for research. So we had the opportunity to look at this tissue. So most of the tissue was fresh tissue, some of it was cryopreserved, and there's a range of ages, and obviously some of them were around puberty, but most of them were prepubertal. Now, this tissue is fascinating tissue. It's very different from the adult tissue, and when you look at the imaging of it, you can see cells for everything. You know, there's nerve development going on there, and it's just very, very active tissue. So you can see here the oocytes within the tissue. And these oocytes that within the primordial follicles in this tissue activate to grow. So you do get activation. And when you dissect out the growing follicles, you find that there's a huge difference in terms of their capacity to grow in vitro. So what we find is that there's an age-related effect in their ability to develop to the next stage. So if we dissect out follicles, of course, this is our adult material. They grow quite nicely in vitro. But the 12 to 15-year-olds, there's a big drop. They don't grow quite as well. And then the really young tissue, well, that's almost, you know, it's growing, but very, very slowly. And we find that there's a difference between the somatic cell component and the oocyte. So our conclusion then is that follicles can initiate growth at all stages or at all ages to the secondary stage, but the tissue from the younger girls and the follicles that have started to grow, they don't grow as well as the follicles that we get from the older women, from adult women. So there is a difference in this type of tissue. And of course, that may well have implications for fertility preservation. And so the question then is, well, what's different about the oocytes or the follicles from the prepubertal girls or the young girls compared to the adult women? And we published this in Human Reproduction. It was published a couple of years ago. And we found when we looked at the morphology of this tissue that there were many oocytes that didn't look normal within the prepubertal tissue or the young tissue. And we found what we referred to as these big fat oocytes. And there were large, enlarged oocytes that did not have a well-defined germinal vesicle. And we only found them, it was an age-related effect. We found them in the young girls, you saw them prepubertally and in around puberty as well, but we never ever saw them in the adult tissue. So clearly the ovary is getting rid of these oocytes by the time the woman is in adulthood. So this is something that we're looking into, and how we can manipulate this process in vitro with the young tissue. Can we somehow eliminate those oocytes and start to look for the functional oocytes? We've also had opportunity to look at tissue that's been treated with chemotherapy, and this was a study that will be published. It's in press at the moment in Human Reproduction, and it will be out in the early first week in December. And we had biopsies from patients that had Hodgkin's lymphoma, and they had received chemotherapy, either ABVD or the opacopdac. And we know that ABVD normally doesn't have a sterilising effect on the ovary. So we were very interested to look at how this tissue might culture as well. So of course we had healthy controls, and we looked at how the microcortex of this tissue would culture. And what we found was that the tissue, or the ovaries that we had that were treated with the opacopdac, when we found that they were very degenerate, and when we tried to culture them, everything just seemed to fall apart. So we couldn't save any oocytes in vitro. The ABVD ones were really quite striking in that they were very different compared to the material that we obtained from age, roughly the same age, had the illness, but they had no treatment. You could see here that the follicles are starting to grow, and they're getting to the secondary stage, and that's the same with our healthy controls. The ABVD patients, their tissue, they could activate growth, but not at the same rate as the healthy or the untreated. And there was very, very few secondary follicles. So this tissue was really quite different in terms of its ability to grow and develop in vitro. And when we looked at this tissue, the ABVD-treated tissue, we found that it actually looked so much different from the other tissue, or from the normal or the untreated tissue. And we saw that, in fact, this tissue looked almost as if it was prepubertal. It looked like it had been rewound to look like younger tissue. And it also, the follicles were behaving as if they were from younger tissue. So this is something that we're investigating further to find out what the process is, what's the mechanism by which this drug regime is working, how's it working, and what's it doing to the oocytes and the follicles. So in summary then, we have a model system to understand the basic mechanisms of human oocyte development. And that's a first, really, because we've relied on our understanding of oocyte development from the mouse system mainly. Its current role is, of course, as a research tool. Other groups are working on this, and they've been able to get meiotic maturation from preantral follicles after a long culture phase. And we're really getting closer, and other groups are too, in terms of testing the fertilisation potential of these oocytes. Now, of course, we still have a long way to go to really understand the process of oocyte development, but as we do more and more experiments and we manipulate the culture system more, we can see that we're getting closer to being able to get oocytes that will be meiotically competent and developmentally competent. And so I'd like to finish and thank the people who do the work, and Marie McLaughlin's a postdoc in the lab who has great skill in terms of growing these oocytes, and other people that have contributed within the lab, and of course clinical collaborators Hamish Wallace, Richard Anderson, Ju Tong of the IVF clinic in Edinburgh, and David Albertini in New York, and I'm sure you've seen David a lot during this meeting. He's contributed to the imaging of these follicles. And thank you very much for your attention.